So welcome to the Trig Review Workshop. I'm thrilled to see some people here who are attending in person and thrilled to see some people who are attending remotely. If you are attending remotely and haven't previously heard this, I'm new to this technology. We seem to have it set up so that you can see and hear me. I can see that there are people attending remotely, but I can't hear you even if you unmute yourself. Not sure what we didn't turn on, but we didn't turn on something that would allow me to hear you. I do have the chat window open. So for those of you who are attending remotely, if you have a question, please just type it into the chat. And I will make sure that I check periodically, and maybe you two can keep me honest. And I do have my chat window right here, so it's hard to miss. But if it looks like I've been ignoring it, you can maybe point out that I've been ignoring it and that that's highly rude and I should be kinder to the students who are attending remotely. Okay, so the topic for today was just going over the 6 graphs of the trig functions. Okay, so I want you to just take a minute and think, if I were to ask you to just graph all 6 trig functions right now, could you do it? And could you do it in 5-10 minutes? Or would it be like this monumental task of taking forever to remember what they look like? Okay. Usually I will poll people. There are only 2 people currently in the room, so I won't actually take the poll. But just kind of nice to know for yourself what your comfort level is with the material coming into this. Okay. The basic graphs without transformations are things that I think you really want to have at your fingertips. You want to be able to just know what they are so that you're familiar with the shapes of the graphs, because we use them for all sorts of things. Okay. So I'm going to start by just reminding you of the unit circle definitions of our trig functions. So if here's the unit circle, and we're going to pretend that that's perfectly round, it's centered at the origin, because we know it's supposed to be, even though my picture isn't particularly good. Okay, I'm going to label this as the capital x-axis, and this as the capital y-axis. Okay. I'm doing that simply because sometimes we call the angle little x, and I don't want to confuse the angle with the capital X value on this coordinate system. Now, to avoid that confusion, I'm going to at least initially just call my angle theta. But I am in the habit, when I draw the unit circle, I just always label my axes now with capital letters, so that if I happen to be calling my angle little x, I have a visual way of distinguishing between little x, the angle, and capital X, which we'll see in a moment is actually cosine of that angle. Okay. So what I'm going to do is I'm going to draw in standard position, which means I'm starting at the positive capital X axis, and I'm rotating in the positive direction counterclockwise. I've just drawn an acute angle here, theta. Okay. I've drawn an acute angle because with an acute angle, I know I can just use SOHCAHTOA. I can use right triangle trigonometry to remember my definitions. Okay. So I'm going to just drop a perpendicular to the capital x-axis here, and then you'll notice that I've created this nifty right triangle. Okay. And because this is the unit circle, I know that the hypotenuse is 1. This point right here, capital X, capital Y, actually tells me the side lengths of this triangle. Capital X is the horizontal side, and capital Y is the vertical side. Now, if I'm in a different quadrant, at least one of capital X or capital Y is going to be negative. So they wouldn't be the actual side lengths, because length can't be negative. Although I could interpret them as the signed side lengths, if I want to label things that way. But here it's nice. I don't even have to worry about whether I'm working with actual side lengths or signed side lengths, because they're the same. Okay. And so now the SO in SOHCAHTOA stands for sine is opposite over hypotenuse. So this picture helps me remember sine of theta is the opposite side is y, the hypotenuse is 1, and that simplifies to just capital Y. So the capital Y value of the point where we intersect the unit circle is sine of the angle. Okay. The ka stands for cosine. So cosine is adjacent over hypotenuse. And I can see that the adjacent side is x, and the hypotenuse, of course, is 1. So I would have capital X over 1, and that simplifies to just x. Okay. So this point, the coordinates of that point are actually cosine theta, sine theta. And if I work with that enough, I just remember that because I've worked with it so often. But what I like is if I forget which is which, I can always get this picture and I can just go back to the basics. If I know SOHCAHTOA, I can figure out the unit circle definitions of things. Let's go ahead and write out tangent as well. Tangent of theta is opposite over adjacent, so that would be y over x. And these definitions, which I derived in the acute case using SOHCAHTOA, these are the unit circle definitions of sine, cosine, and tangent for all angles. Okay. So if I want to graph y equals sine of theta, okay, I'm going to be referring to this picture here in order to draw a picture over here, where this horizontal axis is my theta axis. So I've got a y-axis for the vertical axis, and I'm putting my angle theta on the horizontal axis. Okay. All right, let's see, I'm going to erase these definitions, but I'm going to keep the picture up. Now, very important to recognize that in this picture, we're representing our angles rotationally. Theta is the angle that rotates from here to here. On this picture, we're representing those same angles a different way. We're representing the angles as points on the horizontal axis. So over here, theta increases as I rotate further around. Over here, theta increases just as I move to the right. Okay. So this would be theta equals 0. What I'm going to do is I'm going to mark off my quadrantal angles. Those are multiples of 90 degrees or pi over 2 in radians. And I'm going to work in radians. We're pretty much in pre-calculus. We sort of split our time between degrees and radians. Once you're in calculus, if you're doing calculus, you're working in radians. Now, that's not to say you won't see degrees in your calculus class. You certainly will, okay? But that is to say, if you're doing anything involving calculus, you're going to need to convert to radians to do the calculus, and then possibly convert your answer back to degrees at the end. Okay, so I'm going to go ahead and do that. I'm going to mark off quadrantal angles corresponding to 1 revolution around the unit circle, both here and here. So here, see, I'm going to just move that x over. This would be 0 on the positive x-axis. On the positive y-axis, I've rotated pi over 2, then pi, then 3 pi over 2, and then 2 pi. Okay. So 0 and 2 pi, of course, are coterminal, and I could keep going again and again and again. Okay. Over here, those same angles, I'm going to write just increasing as we go to the right. So 0, pi over 2, pi, 3 pi over 2, 2 pi. Now notice, one thing that's kind of interesting is over here, as I rotate from 0 to 2 pi, I'm going through all 4 of the quadrants. Over here, I'm on the boundary between quadrant 1 and quadrant 4 on this graph, but I'm nowhere near quadrants 2 and 3. But I will often think of this as the interval from 0 to pi over 2 corresponds to angles in quadrant 1. Now, I'm not talking quadrant 1 here. I'm saying if I were representing my angles rotationally, those angles in this interval would land in quadrant 1. Similarly, between pi over 2 and pi, this interval of angles, if I were to represent them rotationally, which I'm doing over here, those angles are in quadrant 2. From pi to 3 pi over 2, represented rotationally, those angles would be in quadrant 3. And then from 3 pi over 2 to 2 pi is quadrant 4. Okay. So that moving from 0 to 2 pi here corresponds to rotating through all 4 quadrants on this picture. Okay. And now I'm going to take advantage of this definition that sine of theta is the capital Y value where my angle intersects the unit circle. So I'm going to just mark that off for these quadrantal angles. So 0 and 2 pi intersects the unit circle here. And that point is going to be 1, 0. I know this distance has to be 1 because it's a radius of the unit circle. And if I'm on the capital X axis, my Y value is 0. Pi over 2 intersects the unit circle here. Again, that's on an axis. I've come 1 up. Since I'm on the y-axis, x is 0, but I've come 1 up. This point here, I know that this distance is 1, but I can see I've gone to the left this time. So that's going to be the point -1, 0. And then this point here is 0, -1. Okay. So what I'm going to do is I'm going to, on this graph here, plot the values of sine of theta for these quadrantal angles by referring to my unit circle. Okay. So when my angle is 0, the Y value where we intersect the unit circle is 0. So sine of 0 is 0. At pi over 2, the Y value where we intersect the unit circle is 1. So sine of pi over 2 is 1. At pi, the Y value where we intersect the unit circle is 0. So we've come back to 0. For some of you, this might be enough for you to finish the graph. If you remember that it's a wave and you just don't remember, where does the wave start? Does it start at a high point or does it start in the middle? This tells you, oh, it starts in the middle, and you might be able to just finish this. If I keep rotating around at 3 pi over 2, which is down here, the capital Y value is -1. And then at 2 pi, I've literally come full circle over here. We're back to our Y value of 0. And so then I can connect the dots. Now, if this was my first time graphing this, I might think I just connect the dots with straight line segments and have all sorts of sharp corners. I've done this before. And the first time I do it, I would probably plot some intermediate values like pi over 6 and pi over 4 and pi over 3. Having done it before and just reviewing it, I know that it's a nice curve. So what I've just graphed here is one period of the sine graph. I do want to make sure I indicate that it keeps going. So I'm going to make sure I've got arrows on the end. Otherwise, I'm implying that the domain is just everything from 0 to 2 pi and nothing else. And I actually know that it's more than that. Okay. So that's my sine graph. And it's often called a sine wave because it does look like a wave. And that's a lot of its useful applications are in studying things that travel in waves. Okay. And very often people remember that it's a wave. They just don't remember where it starts. But using the unit circle and just saying, oh, sine is the capital Y value, I know it's going to start here at the origin. Okay. Now, I think the 6 trig functions kind of come in pairs. So there's sine and cosine, and their graphs are very, very similar. Okay, so I just graphed for you sine of theta. What I want you to do is I'm going to give you a few minutes to graph cosine of theta. Okay, I think what I'll do is I'm going to pause the video recording so that you don't have all this blank time. If you're watching the video, just pause it, draw cosine, and then turn it back on. If you're currently attending, take a moment, draw your cosine graph. Okay, I've turned the video back on. I don't know if the folks at home have finished or not. If you haven't, that's totally fine. Anytime I give you something to work on in your seats in class or in one of these workshops, I'll give you some time. I'm not necessarily giving enough time that I expect everybody to finish. So don't feel like there's anything wrong with you. If you didn't finish, you at least got to get started thinking about this. Okay, so now I want to graph cosine of theta. So again, on the axis here, I just marked off my quadrantal angles corresponding to 1 revolution around the unit circle. And again, I'm just going to use my unit circle over here. So when my angle is 0, this time I'm looking for the capital X values. So when my angle is 0, cosine is 1. When my angle is pi over 2, the capital X value is 0. So we come down and hit the horizontal axis there. When my angle is pi, my capital X value is -1. At 3 pi over 2, the capital X value is 0. And then at 2 pi, we're back at our starting point at a value of 1. Okay. And then I just want to connect the dots. I know this is going to be a nice wave shape. And again, I want to make sure that I've got arrows on the end to indicate that the pattern continues. Okay. And if you're doing this as a homework problem or on an exam or a quiz, just make sure you read the directions. What I'm drawing right here is 1 complete period. Basically, this is the thing that cosine does. And then it just does it again and again and again. And it goes on forever and ever in both directions. Okay. Very often, homework problems might say graph at least 2 periods. And that just says, hey, it's going to do this again, draw another complete pattern, et cetera, et cetera. I'm just sort of reviewing the basic pattern. So I'm contenting myself with 1 period right here. One thing to note with our starting and ending points, which are sort of contrived, because of course the graph doesn't have a starting point or an ending point, it just goes on forever and ever and ever. It's very easy if I'm saying I want to draw an arrow at the end, to draw my arrow like so. And that's actually a mistake. It's a really easy one to make, but this is the highest we can ever go. Because if you look, that's the furthest to the right our capital X value can ever be. We never go past that. So I want to make sure I indicate that that's a high point. So I want to show that it goes on forever and ever, but it goes on forever and ever repeating this pattern. And so what is it doing before that high point? It was coming up to it. So I want to make sure on either end that I indicate that these were high points that I have here. Okay. So sine and cosine are both waves. Their period, which is the length of the interval over which it does its thing once. So it repeats a pattern. The length of the interval over which it does 1 cycle corresponds to a full revolution around the unit circle. And so that's 2 pi. So every interval of length 2 pi, sine and cosine are going to do their wave thing. A lot of times people remember that, but just get confused about which one starts where. So cosine starts at its high point, sine starts at the origin on its way up. At some point, you may accidentally memorize that just by being so familiar with the graphs and working with them so often. But if you ever forget them, sine is the y value. it starts at 0. Cosine is the capital X value, it starts at 1. It's all right there in the unit circle. Okay. All right. So does anybody have any questions on either of those graphs, sine and cosine? I'm gonna erase this and give the people in the chat time to type in questions if they have it. If I don't see any questions, we'll move on to tangent. Okay, so let's graph tangent. And I'm going to just remind us that since tangent was TOA, that's opposite over adjacent, that's going to be capital Y over capital X. So notice capital Y here, the top of this fraction, is not the same as little y, which is the output of my tangent function. Little y is what's going to be on the vertical axis of this graph here. Okay. Now, I'm going to pretend I don't know what the graph of tangent looks like. So I'm going to go ahead and mark off the quadrantal angles that correspond to 1 revolution around the unit circle. Because I know all of my trig functions are going to repeat themselves every time I go around the unit circle. Turns out some of them repeat themselves more frequently than that. But I know for sure that if I can go from 0 to 2 pi, I'm going to have a pattern that will repeat itself. So I'm going to mark off 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so if I look at 0, so the angle of 0 puts me at this point right here, capital Y over capital X would be 0 over 1. And of course, it's fine to have 0 on top of a fraction. That just gives me 0. Now I come to pi over 2, and we're going to hit a problem. Because if I come to pi over 2, capital Y over capital X would be 1 over 0. And you'll notice I'm not even going to write that down. If you're a student in my class, you know that if you do write that down and don't cross it off, I will take points off because you have written something that is not defined. Okay. Now, if you were to write it and then cross it off, I'm fine, because that says, oh, I know I'm not allowed to do that. I can't divide by 0. But I can't divide by 0. Okay. So pi over 2, tangent of pi over 2 is not defined. Okay. But I can see that for any angle close to pi over 2, like an angle here or an angle here, my x value isn't going to be 0. It's just going to be a very small number. Maybe a positive number, maybe a negative number. Positive here, negative here, but just a very, very small number. And my capital Y value is going to be close to 1. So I can say close to pi over 2. I'm getting a fraction where the top is close to 1 and the bottom is close to 0, meaning that the bottom is really, really small. Now, what happens when you divide by something really, really small?
Really big?
You get something really, really big. Okay. Those of you in calculus have probably learned that as you're taking limits, if the bottom of a fraction goes to 0 and the top doesn't, that's a sure sign that you're getting a vertical asymptote. Okay. And if you're not yet in calculus, that's okay, because this answer was just given to us by one of my pre-calculus students. When you divide by something small, you get something big. So we're going to have a vertical asymptote at this point, meaning that the function's either going to go way high up towards infinity or way high down towards negative infinity. Okay. At pi, much nicer one. Capital Y over capital X is going to be 0 over negative 1. That's just 0. But at 3 pi over 2, we're going to have an issue again, because if I tried to follow the definition, it would put 0 in the denominator, and I know I can't have that. But we've just learned what happens at that point. We're going to have something close to negative 1 divided by something really, really small. And when you divide by something really, really small, you get something really, really big. So we're going to have a vertical asymptote there. Okay. And then at 2 pi, we're back coterminal with 0. We get 0/1, which is just 0. And so usually at this point, I've plotted some points. And I see now it's time to connect the dots. Well, we can't really do that because this dot and this dot aren't going to connect because they've got an asymptote separating the graph into different pieces. Where I want to remember that this interval of angles corresponds to angles that when I represent them rotationally over here, between 0 and pi/2 are in quadrant 1. So this interval of angles corresponds to angles in quadrant 1. Between pi/2 and pi, that corresponds to quadrant 2. Then 3, then 4. So that moving from 0 to 2 pi here, just moving to the right, corresponds to rotating from quadrant 1 to 2 to 3 to 4. I'm going to use that because I know that with vertical asymptotes, my function is either going way high up toward infinity or way low down towards negative infinity, but I need to know which one. So in quadrant 1, is tangent positive or negative? Positive. It's positive in quadrant 1. Okay. Because again, it's capital Y over capital X, and both of these are going to be positive in quadrant 1. So if it's positive and getting big, I know it's going to be going up towards positive infinity. Okay. Now, if I look in quadrant 2, so between this asymptote and this 0, because with my quadrantal angles, I sort of alternated 0, asymptote, 0, asymptote. So I want to know how we go here. In quadrant 2, is tangent positive or negative?
Negative.
It's going to be negative because again, it's capital Y over capital X. In quadrant 2, my Y values are positive, but my X values are negative. And a positive over a negative is negative. So I'm going to draw this backwards, starting at the 0. Drawing it backwards, we're going down towards negative. Now, I sort of emphasized that I was drawing this backwards because if I were actually describing the behavior of the graph, I want to remember we always read graphs left to right. The function is actually increasing here. I just find it easiest to draw things starting at the point that I know and then going either up or down. So if the point's in the middle and I'm going towards negative infinity, I'm going to say, okay, I'm going to decrease to negative infinity. All right, the next interval corresponds to quadrant 3. In quadrant 3, is tangent positive or negative?
Positive.
It's positive because now both the capital X and the capital Y values are negative, and 2 negatives are going to make a positive. So here we're going to go up towards infinity. And then this next little interval corresponds to angles in quadrant 4. In quadrant 4, is tangent positive or negative? Negative. It's going to be negative because now our Y values are negative, but our X's are positive. So again, drawing it backwards, I'm going to go down towards negative infinity. So this is what I get if I just graph what I see from 0 to 2 pi. Okay. I don't like the graph that I just drew, okay? Because I know it's repeating a pattern, and this pattern, it's really nice to see. This kind of looks like the right half of that pattern, and this kind of looks like the left half of that pattern. I'd rather have full copies of that pattern. So I always, when I'm graphing things, will start and end my graph at an asymptote. For those of you in my class, you can expect directions if I ask you to graph a trig function to say if there are asymptotes, start and end at an asymptote. For those of you who have other teachers, make sure you just see what their standards are for graphing things. But I know I always require start and end at an asymptote. So I sort of naively started at 0 and ended at 2 pi because I was just going around the unit circle. I'm going to say, okay, if I were to go backwards, This would be negative pi over 2 would be the next quadrantal angle. And notice between negative pi over 2 and 0, that corresponds to quadrant 4. That kind of makes sense because as we move around the circle, we go quadrant 1, 2, 3, 4, then we're back to 1. So what comes before 1 is 4. Okay. And in quadrant 4, we determined that things were negative. And my next quadrantal angle over here would be at 5 pi over 2. This interval corresponds again to quadrant 1, where tangent is positive, so we're going up. I think that just looks a little bit cleaner. Now I can see, oh, look, it looks like it's the same pattern repeated 3 times. And in fact, this shows 3 periods of tangent. So tangent will go through its cycle, its pattern or its period twice as we rotate once around the unit circle. What it does in the first 2 quadrants, it repeats in quadrants 3 and 4. Okay, so the period of tangent is pi. So over every interval of length pi, tangent will do its thing and do its thing exactly once. Now, this is a very rough sketch. If I wanted to improve upon this to sort of get how steep it's going to be in the middle, I might plot some intermediate points. So I might plot the values at pi over 4, or maybe pi over 6 or pi over 3, just to see exactly how it curves. But just to remember that that's the pattern for tangent, I figure out where the zeros are by where the capital Y value is 0. Because if it's y over x, that's going to put 0 on the top of my fraction. I figure out where the asymptotes are by where the capital X values are 0. So notice basically at every odd multiple of pi over 2, I'm going to have an asymptote. Now, a lot of people will remember that tangent's the one that's always going up. So if you just remember that, you know where the asymptotes and the zeros are, you can sketch it. But if you ever forget, this interval corresponds to quadrant 1. The fact that tangent is positive tells me we've got to go towards positive infinity, not negative infinity. Okay, so I'm going to pause the video again. I'll still be here. I can still monitor the chat for those of you at home, but I'm going to have you folks graph cotangent of theta. And see if you can figure out, if you don't already remember, what the period is. And for your graph, I will ask that you start and end with an asymptote. So I suggest you do what we did. Start at 0, go to 2 pi. And then if you need to adjust, you can adjust. And you might not need to adjust. We'll have to see. Okay. But I'm going to pause the video. I can still check the chat for those of you at home if you have questions. Okay, I've got the video turned back on and we'll go over this together. Again, for those of you at home, if you didn't finish, don't worry about it. There's nothing wrong with you. Everybody works at slightly different paces. I'm just trying to make sure that everybody has a chance to get started on things and nobody's sitting around waiting for too long. Okay. So cotangent is just the reciprocal of tangent. So if tangent was y over x, it's going to be capital X over capital Y. So I'm going to basically do the same thing. At 0, I'm going to come over here and I'm going to say capital X over capital Y. Ooh, that would put a 0 on the bottom. So I've actually got a vertical asymptote there. Now I've already got the y-axis drawn in as a vertical line. So I just sort of have to make a mental note that that's going to be a vertical asymptote. Or sometimes I even write myself a little note to just remind myself. Not necessary, but just because I'm thinking that now and I'm not drawing the entire graph now, I sometimes will write myself a note. Okay. All right, at pi over 2, capital X over capital Y is 0 over 1, which is 0. At pi, we run into a problem again because capital Y is in our denominator and that's 0. But we've learned when you divide by something small, you get something big. So we can't actually divide by 0, but close to 0, we're dividing by something small, we're getting something big, and graphically that's going to mean we have an asymptote. Okay. It is necessary, if your asymptote doesn't overlap with the line that you've already drawn, that you draw it in as a dotted line. Okay. One thing I've noticed over the years, students 15 years ago always drew in their asymptotes as dotted lines. As graphing calculators and computer graphing programs became more common, students became less likely to draw in their asymptotes. And that's actually a drawback of the technology. So I'm pleased that technology is allowing me to talk to those of you who are at home right now, because we've got more people attending virtually than in person. But technology, when it's drawing graphs, doesn't draw in the asymptotes. And when you're drawing things by hand, it is necessary to draw them in. Okay. All right, 3 pi over 2, capital X over capital Y is going to just be 0 over -1, and 0 over any non-zero number is just 0. And then at 2 pi, we're back to a problem. This would put 0 in the denominator. So I know the function is undefined at 2 pi, but close to 2 pi, it's big. So once again, I get this pattern that we alternate. Asymptote 0, asymptote 0, asymptote. What's nice is with this one, just going from 0 to 2 pi, I did already start and end at an asymptote, so I don't need to adjust. But now I am going to think through, this interval corresponds to quadrant 1, 2, 3, and 4. So I can use the plus or minus sign of cotangent to figure out whether we're going up towards infinity or down towards negative infinity. So I know in quadrant 1, everything is positive. So starting at this 0 and drawing it backwards, I'm going to go up towards infinity. Of course, if I read the graph left to right, it's actually a decreasing function here. In quadrant 2, this fraction is going to give me something negative because now X is negative, but Y is positive. So we're going to go down towards negative infinity. In quadrant 3, cotangent is going to be positive because it's a fraction of 2 negative numbers. So again, drawing it backwards, I'll be going up, although notice reading left to right, it's a decreasing function. And then in quadrant 4, now X is positive, but Y is negative. So we're going to go down towards negative infinity. And it looks like it's done its thing twice, and it has the period of cotangent is 2 pi. I'm sorry, my bad, is pi. So there are 2 periods in 1 revolution around the unit circle. Okay, and you might remember that cotangent always goes down, in which case knowing where the asymptotes and the zeros are is enough for you to fill in the graph. But again, if you forget, you can use the fact that these intervals correspond to quadrants to figure out whether your function is positive or negative. Okay, so you'll notice tangent and cotangent are very similar. Tangent always goes up in between its asymptotes. Cotangent always goes down in between its asymptotes. The asymptotes are at different places, but the reason is because each of them is a fraction. Tangent has capital X in the denominator. Cotangent has capital Y in the denominator. So you can figure out where your problem points are by where the variable that's in the denominator would be 0. Okay. If there are any questions on tangent or cotangent, this is a good time to ask them. I'm going to erase the board. I'll check in the chat. Don't see any questions at this point. So we've got 2 more to go. And of course, they go in patterns. So these are going to be very, very similar. So I want to take a look at the graphs of secant and cosecant. Let's actually start with cosecant. So if I look at y equals cosecant of theta, now I could define that in terms of my capital X's and Y's, but I'm actually just going to say that's the reciprocal of sine of theta. Okay. Now, of course, that means it's the reciprocal of my capital Y value, because that's what sine of theta is. But usually, what I do to graph secant or cosecant is I start with the function that it's the reciprocal of. So what I'm going to do is on my theta axis, again, I'm going to just go through 1 revolution around the unit circle. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm going to actually graph the sine function, one period of the sine function, but I'm going to draw it as a dotted curve because the points on the graph of sine, for the most part, are not going to be on the graph of cosecant. This is just going to help me to visualize what its reciprocal will look like. So sine, I know it's one of those waves. If I remember that it starts at the origin, great. If I've forgotten, I come over here and I say, oh, sine is the capital Y value. So it's going to start at 0, and at pi over 2, it's going to go up to 1. So I sort of mark off those points. And now I'm just connecting them with a dotted curve. That's not actually my graph of cosecant. This is just to help me figure it out. But what I like about this is this shows me exactly where sine is 0. And I know that where sine is 0, cosecant is going to be undefined. Those values are not in the domain of cosecant, but I also know what happens there. Because as I'm close to those points, I've got 1 divided by something very, very small. And once again, if you divide by something small, you get something big. It's amazing how often that's a useful fact. That's going to tell me that I've got a vertical asymptote on the y-axis and at pi and at 2 pi. And you'll notice these asymptotes divide the sine curve up into this interval. It actually corresponds to quadrants 1 and 2 because it's going from 0 to pi. But this interval where sine is positive, and then this interval, which corresponds to quadrants 3 and 4, where sine is negative. Now, if I take the reciprocal of something positive, I'm going to get something positive. So I know that between these two asymptotes, my graph is positive. And if I take the reciprocal of something negative, I'm going to get something negative. So I know that between the next two asymptotes, my graph is negative. Okay. Then I want to think, what happens with reciprocals? And with reciprocals, it sort of changes the size of things. The reciprocal of something small is big, and the reciprocal of something big is small. So if I look here, I'm going to refer to this as a bump on the sine graph. And this particular bump is a positive bump, and it goes from small positive numbers to the biggest positive number that we hit on sine, which happens to be 1, back to small. So the pattern here is small to big to small. So if I take the reciprocal, the pattern is going to be big to small to big. Starting and ending big makes me feel good about having asymptotes. That's what asymptotes tell me I do. And let's figure out, in the middle, I'll be taking the reciprocal of 1. What's the reciprocal of 1?
1.
It is 1. Oh, this is so exciting. So we start out big, come to the lowest value on cosecant, which happens to be the highest value on sine. So the helper graph, which was sine, and the actual graph of cosecant just touch at that one point. The high point on sine is the low point on cosecant. Okay. Over here, I've got a very similar pattern. These are negative, but if I look at the size of the negative numbers, we go from a small negative number to the biggest negative. The most negative number we hit is -1, back to a small negative. So keeping things negative, if I take the reciprocal, it's going to go big negative to small negative to big negative. And once again, the reciprocal of -1 is -1. So here, the high point on the graph of cosecant will match the low point on the graph of sine. So what we have here is it looks like alternating parabolas. These aren't actually parabolas because parabolas are infinitely wide, but they're the same basic sort of U shape. So we've got a U that opens up followed by a U that opens down. That's the pattern. And so the period of cosecant is 2 pi. One period is 1 positive and 1 negative. I like to refer to this technique of graphing as just flipping the bumps. Draw your sine curve as a dotted curve because it's not part of the actual graph. Notice if I drew this as a solid curve, I'd be suggesting that that was part of my graph, and then I'd be failing the vertical line test, so I wouldn't be drawing a function anymore. But here, this is just for me, this is just helper stuff. Okay, here's my actual graph. Okay, and what I did is I drew the initial sine curve. Wherever sine was 0, cosecant was going to have a vertical asymptote. That divided things up into positive bumps and negative bumps, and then we flipped the bumps. Pretty cool. Okay. Notice with cosecant, we do have asymptotes at 0 and 2 pi, so I get for free that I started and ended at an asymptote. I'm going to once again pause the video and ask you folks, either in your seats or at home, to try to graph secant, which is the reciprocal of cosine. And this one you will have to adjust so that you can start and end at an asymptote. I don't care how many periods you draw, but start and end at an asymptote. Oh, let me pause the video and go over this just because we're almost out of time. So since this is the reciprocal of cosine, I'm going to do the same thing I did when we did the reciprocal of sine, which is I'm going to start by graphing a cosine function. And cosine was the one that started at its high point. Remember, cosine is the capital X value, so it starts at a value of 1. I'm going to draw this as a dotted curve. And then again, since cosine is in the denominator, anywhere cosine is 0, secant's going to have a vertical asymptote. So I've got one at pi over 2, at 3 pi over 2. And I'm going to go ahead right now, since I know I gave the directions of start and end at an asymptote, I'm just going to continue this to 5 pi over 2. Which is the next place where cosine would be 0. So there's an asymptote there. And I'll extend this to the left to negative pi over 2. Cosine would be 0. So secant has an asymptote there. And so again, the asymptotes divide the graph up into bumps. I haven't done a very good job of drawing to scale. These should actually be evenly spaced. So just use your imagination and pretend I'm better at spatial recognition and that these are evenly spaced. Okay, positive bump, negative bump, positive bump. And all the bumps, if I look at the absolute values, go from a small value close to 0 to the biggest value, the one that's furthest away, back to small. Small negative to a bigger negative, back to a small negative. Small positive to a bigger positive, back to a smaller positive. So then when I flip the bumps, I'm going to get this. And again, just like with cosecant, the low point here is going to match the high point on the original function because the reciprocal of 1 is 1. And here the reciprocal of -1 is -1. So the high point on secant matches the low point on cosine. And we flip this. Now, what I've graphed here is 1.5 periods. Because a full period would be 1 positive u and 1 negative u. Okay, so the period of secant is 2 pi. Okay. And again, if you're asked to actually graph something, very often the directions will specifically say, draw exactly 1 period or draw exactly 2 periods. Or sometimes they'll say, draw at least 2 periods or something like that. So just make sure you're reading the directions on things. What I've tried to do in this workshop is just walk through the basic 6 trig graphs, but give you some tools so that you don't have to just memorize them. Probably with sine and cosine, you work with them so often that at some point in your math career, and it may have happened to you already, and maybe it'll happen tomorrow or next semester or next year or whatever, you'll just kind of know them because you worked with them a lot. Okay. But if that hasn't happened yet, I gave you some tools so that you can try to figure them out from using the unit circle. Okay. We tend to work with the others a little bit less often, but they're still very, very important. And it's nice to have the graphs at your fingertips, but that doesn't mean create flashcards and memorize them, because I have found that what often follows memorization is forgetting. Okay, so hopefully these tools will help you understand the graphs a little bit more so that you can have them at your fingertips by thinking through the process rather than just having them memorized. So, and that's how I encourage you to approach trig in particular, but all math in general. The more you can understand it, the easier it is to remember, and the more rewarding it is. Because, just memorizing a bunch of stuff, it's like, you don't feel good about that, but understanding something feels a lot better. So hopefully you're leaving with some understanding here. I'm going to thank all of you for attending. I just checked, and a minute ago we had 16 attendants virtually and 2 in person. So I'm thrilled that there were 18 of you plus me. That's 19 people who got to play trig today. And playing trig is one of my favorite things to do. So I'm going to end the video now, but I will keep the Zoom session on so that if anybody does have a question, I'll be here for a few extra minutes. Please just type your questions into the chat if you have them.